class, we said, there's a capacitor here. And they said, oh, do we need that capacitor? And I said, oh, no, you don't need that. And I thought about some more. Well, you actually do need that capacitor. And the reason you need that capacitor is when the clock changes, so that, you turn off this transmission gate and you turn on this one, then this doesn't happen instantaneously. There's some delay from these gates turning off and on. And this capacitor assures that it remembers the old state before the feedback path kicks in. So technically you do need a capacitance there, and it comes about automatically because of this gate. So yeah, you actually do need that capacitor. For anybody that's interested. Okay, so back here, we started talking about field programmable gate arrays. So today we're going to learn about what's inside these FPGAs you've been programming all along this semester, this last part of the semester. So the FPGA has three main blocks. There's these things called CLBs. There's these things called switching matrices, which kind of switch signals. And then it's not shown here, but there's some IO blocks as well. And the way it works is in these CLBs, there's flip-flops and logic, and you can program that logic, and I'll explain how you do that, but you program that, and these signals come out onto wires, and they go into this switching matrix, and this switching matrix is just a bunch of switches that route it to different, they route the connections. So the kind of like the connections are like, okay, let's say you have a CLB, and inside the CLB, there's, let's say there's an AND gate. And it comes out and it connects to this switching matrix. And the switching matrix, there's like a cross point of switches, but there's, say, a little switch here that can connect you to this node. And this node comes out here, and it goes into this other CLB, and maybe has a NOR gate or something, right? So because you're going through switches, and those switches have, a resistance, and then there's capacitances on these lines, they tend to be much slower than if somebody's making noise. Okay, gotta mute everybody here. Let me do that again. Oh, stop. Okay. Anyway, because these switches have resistance and capacitance, there's delay along here, whether if you just had a wire, it would have almost zero resistance. So these switches that make the connections are great because they're programmable. You can reprogram these switches to reconfigure your circuit, but they tend to make things much slower than if you were in an ASIC. In an ASIC, you wouldn't have this switch. This would just be a physical wire. So that's an important concept. Why FPGAs? Like an FPGA, if you get it to go like 100 to 200 megahertz, that's pretty good. That's pretty high speed. Whereas an ASIC, it's like 1 to 2 gigahertz is more common. So, an ASIC is like 10 times faster. So you can make it much higher performance and lower power, it turns out, from these wires. Okay, so that's kind of like the way it works. Some concepts here, there's short turnaround time. So instead of fabricating an ASIC where you have to send it off, get it manufactured, and come back, you just reprogram it to do whatever you want. So it's like almost instantaneous turnaround time. It's repeatable. You can reprogram it. It's ideal for prototyping because, again, you can change things on the fly. Switch matrix for disjoint cells and global interconnects. We'll talk more about that. It's volatile, though, for the FPGAs that we're using because these connections, I didn't show it here, but how do you make that connection? Well, that connection is connected to a little RAM cell. Put a little R here. And that's what, when you download a bit file, there's a whole bunch of these little, it might be another switch here that connects to another CLB here. And it has its own little RAM cell. And these little RAM cells are all connected together. And when you download a bit file through the pad, basically you're downloading a daisy chain of signals to program all these little RAM cells to configure the connections. And not only do they configure the connections, they configure these blocks to do a certain logic. And we'll talk about that. So that's kind of the basic idea behind FPGAs. So these SRAMs, there's SRAMs inside the chip. They're actually used for three things. They're used for what are called lookup tables. and we call those LUTs. They're used for embedded RAM blocks and to control the routing. So we just talked about the control the routing. So the RAM cells here, these were to control the routing. The lookup tables is a little more complicated. I have a picture. Maybe we should talk about that. So I don't know if you remember, we did an assignment back a while ago where you, assignment 2, I guess you guys submitted it now, where you basically had a lookup table. You had this function. I can't even remember what the function was. It was like y equals x squared plus 3 or 4, or was it a squared plus 4a or something like that? But you basically had to make a lookup table. You basically had some x, you had like this case x, and if x is 0:0, 2-bit binary 0, then you got, y equals 0. If it was 0, 1, it equals 2 or whatever. Basically, you were making a lookup table. For some given values of x, you got some given values of y. And that's kind of fundamental. Well, sorry, that's a lookup table. And that is how we build logic in FPGA. So to think about this, let's make a little memory. So we're going to use a memory for the lookup table. And I'm going to make a memory that looks like this. I'm going to give you an example. I'm going to have 8 cells in here, okay? So here's my 8 cells. And that's my memory. And the memory is going to need an address decoder. We've done decoders all before here. This is a decoder. And the decoder, in this case, since there's 8 possibilities, will have 3 bits. And that will select one of those bits. Oh, you know what? We'll do a different one. Sorry, we'll do a different one. Hold up. There's kind of 2 ways to do this. We'll do it this way. We'll make a mux instead. Let's make a mux. And we'll have 3 bits going into this mux and 1 bit coming out. And we'll have 8 bits going into this mux. Okay. And let's say we wanted to make a 3-input NAND gate. If you were to make a 3-input NAND gate, and we looked at the possibilities here from 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1, you would say for a 3-input NAND gate, the only time we get a 0 is 1, 1, 1 will give us a 0. Any other combination of the inputs will give us a 1. So if I put in this memory 0, 1, 1, 1, 1, 1, 1, 1, and then instead of making these 3 inputs to a real NAND gate, I make those if I called this in 0, in 1, and in 2, instead I'm going to feed them into this mux. In 0, in 1, and in 2. So if I put a 1, 1, 1 here, it would say, oh, let's select this address up here, and it would feed that 0 to the output. If I put any other combination of 1, 1, 1, it would feed one of these other ones, and I would get a 1. So this memory and mux works the exact same way as this NAND gate, okay? Now, it wouldn't be great because how many transistors does a 3-input NAND gate have? It has 6 transistors, right? How many transistors does this have? Well, each one of these memory cells is like a little latch. We learned how to make a latch before, right? We just need 2 inverters and an access signal, right? That's a latch. So each one of those is a latch. So they have 2, 2, 1. There's 5 transistors in each one of these little cells. And this mux, if I want an 8-to-1 mux, what's an 8-to-1 mux? It's 7 2-to-1 muxes, right? We learned that before, right? If you have 8 inputs, it's to the end. So that 8-to-1 is like a 4-to-1 and a 4-to-1 and a 2-to-1. And each of those 4-to-1s is a 2-to-1s. 2-to-1, right? So that's, this one's got 3 and this one's got 3 and that's one more. So there's 7 of them, right? And each one of those 2-to-1 muxes has a NAND. The easiest way to make it is 3 NAND gates like that, right? And an inverter. So each one of those muxes has, each NAND gate here is 4, 4, 4, and 2. So that's 14 for the 2-to-1 mux. And we have 7 of them. So if I did the total number of transistors, I'd have 7 times 14 for this mux, plus, now I have 8 times 5 for these memory cells. What's that equal? 70, 98 plus 40, that's what's that? 138 transistors, all right? So this has 138 transistors. This only had 6. So you tell, why would you ever want to build a 3-input NAND gate using some memory and a mux? Well, the reason you would do it is because, well, what if I said I don't want a 3-input NAND gate? What if I said I want a 3-input NOR gate? Well, then the 3-input NOR gate, only when this is 0, 0, 0 does this go to 1. Any other situation, it would be a 0, right? So this has, instead of putting the memory in here like we just did, let's erase all this memory, and instead we're going to write into this memory when it's 0, 0, 0, we're going to put a 1 here, and everywhere else we put a 0. And guess what? We just rewrote this memory, and now we've got a NOR gate. That's pretty cool. Using this little lookup table, and it turns out we can build anything of 3 inputs. If you wrote a circuit like, XOR, I have 3 inputs here, and I have a NAND here, and I have this output comes in here. I don't know, make whatever you want up, whatever you want. If it's only got 3 inputs and 1 output, I can represent it with this memory and a mux. So if you think about it, if we go back to our first picture here, inside here, these configurable logic blocks, they don't have real NAND gates. What's in there is a little lookup table. It's got a little RAM and a mux. And so when you download into these memories, you also, these are a bunch of little R's, right? Each one of these is an R. So yeah, it loads in. It's kind of like this sequential path. Let's go through here. And we write all those. We write these. So by downloading your bit file, you're programming all these lookup tables to form the logic, and you're programming these switches to make all the connections between them. This is kind of cool. So by downloading this, you can change any of the logic, and you can change any of the configuration for the wiring. That's the basic idea behind an FPGA, how you can make any kind of functionality. Coming back here, so we said there's lookup tables for the logic. So we just explained that. We have control routing for the switches. And the other thing is we have embedded RAM blocks. So in addition to this, sometimes we want just some memory for doing whatever, storing values or making lookup addresses or something. So in addition, there's also, let's call it a RAM block. There's also RAM blocks that you can route into these switches as well. and they can be programmed from the pin as well. And this could be like, 1K of RAM or something, or even bigger blocks. So you can load those in with the bit file. So you have memories, you have logic, and you have routing switches. It's easily changeable, like you can dynamically configure it. It uses the latest technology in SRAMs and logic. It's volatile, so that's not great, but you can always download a file. And normally what's done, what you've been doing in the lab is you create a bit file and you download it. But once you're happy with everything, you can just store it in a little EEPROM. And then when it powers up, it reads that EEPROM automatically. So in real life, when you have a product, you've decided on what the final thing is. You have, and you'll notice this, if you go look on the board in the lab, you have your Fpga here. And then off to the side, there's this teeny little chip. That's an E² prom. And then there's also this connector. This is where you're downloading the bit file from this is your PC over here. So you can download here through the bit file. But it turns out you can also use that bit file to program this E² prom. And once E² prom is done, you don't need you can get rid of the connection to the PC. It powers up and it just reads the file from the E² prom. So it can be programmed either way. Yeah, so that's what the SRAM programming does. Any questions about that? Okay, so that's a fundamental. Now there's a little bit more to it than that.
Sorry, I did actually have a question. If you could go back to the previous diagram.
Yeah. This one or that one?
The one that you drew by hand
Oh.
with the E² prom.
Yep.
What is that block in like right after the P? Yeah, that one there.
Oh, that's just a connector.
Oh, okay.
In our case, I think we're using a USB connector, and it goes in. There's actually a little chip on there that takes USB and it puts it into I²C or something, some serial programming thing.
Okay.
So this
cool.
is kind of like USB. There's a connector plus a chip actually, and then it comes out of there as I²C, which is another like serial communication protocol.
Okay, thank you very much.
Yep. Yeah, so let's go back here. So on the Fpga, it's a little bit more complicated than that. So what we've been talking about is kind of like one of these little blocks. It has some logic and it has some interconnect that we can route onto these interconnect wires. But there's other kinds of blocks. There's lots of these, literally thousands, tens of thousands. Some chips have millions of them. So there's lots of logic on there. Sometimes they have just things like this, Fpga clock generators, which you've been using already. Sometimes they have like DSPs for doing digital signal processing. Sometimes they have big blocks of memory. So there's different functionality in each of these sort of grids on the Fpga, but they can all be connected with this programmable interconnect. The config is like the external that configs all the memory. There's also these I/O blocks, which are configurable that pass signals in and out. Yeah. So INT means interconnect and MEM means memory. Yeah. And we'll talk about this. So that's kind of like at a high level. The configurable logic blocks, we kind of talked about this. There's a little more than just the lookup table. Normally you have a lookup table. This is an older generation of AMD or Xilinx configurable logic block, but it has two lookup tables, this one. And each of these lookup tables has 4 inputs. So it can do any function of 4 inputs. So it would have like 16 memory elements, but there's 2 of them. And they can be muxed together with a configurable bit here. And so together you can actually form any 2 functions of 4 variables or any 1 function of 5 variables. And then these outputs F and G can either be routed directly to the output by controlling these muxes. And again, these muxes are controlled by little memory elements, little RAMs, right? Every one of these things that shows like a mux is basically controlled by a RAM cell that you downloaded. Anyway, you can bypass this flip-flops and feed them directly to the outputs if you just want logic. But if you want clocked logic in the synchronous system, you can feed them through these muxes into flip-flops and pass them to the outputs. So this one CLB can have any functions of 4 inputs, 2 functions of 4 inputs, or 1 of 5, and it has 2 outputs that can come out of here. And they can either be clocked outputs or direct outputs. So that's an example of a CLB. And different companies call them different names, but that's a common name. This is a little more detail what's inside of that lookup table. So that's this block right here, right? If you look inside of it, it's a little more complicated. It's got this little latch array, which I explained, and this mux to send it out. But I was showing you when you read it out, you also have to write to it. So when you write to it, you need a decoder to select which of the cells you're going to write to, and then you have to have a write pulse. So my picture was a little simple here. So I drew it like this, but we also need.
Is the storage element also part of the CLB?
Is the what?
The storage element?
Yes. The CLB has, I'm just gonna, there's actually an address decoder here too. So I was drawing this first. This is for writing, okay? The decoder writes in. And so the decoder also has 3 bits, and it selects one of the cells to write. And the select is what controls, oh, I erased it, did I? Oh, I had a little RAM cell. So a RAM cell looks like this. There's 2 versions. You either have anyway, this select cell comes out of the decoder. That select cell is like that, right? Anyway, this decoder, it's a 3 to 8-bit decoder, and we know we've already built these. A 3 to 8-bit decoder would need 3 input AND gates, and you would need 8 of them, right? 1 for each of the bits. And so that would be what's a 3 input AND gate is 8 transistors, right? So in fact, down here we need plus for the decoder 8 times there's 8 of them. So this is 138 plus 64, which is 202. Is that right? Something like that. So it's even worse. We went from 6 to 202. So it's like 2 orders of magnitude, or almost 2 orders of magnitude higher, but it's programmable. Yeah, so we need this decoder and write this. So back up, we had 2 of these blocks, and here's what they look like. There's 1 block here at the top. It has 4 inputs. In this case, these are the 4 inputs. And there's 1 output. And then there's 4 inputs here, and there's 1 output here. Yeah. And those address inputs can either go to the write decoder to load it, or they can bypass that and go to the mux to feed the output. Now, this does not include the flip-flops. In addition to that, there's these flip-flops in the CLB as well, and these programmable muxes. This is just showing this part over here, these 2 blocks. Okay, that's the basic CLB. Usually the FPGA is divided into slices. And so the CLBs have a LUT. This is kind of like an older generation. They built them like this with just these flip-flops, but they kept adding more stuff to it when they realized they wanted to do more things. So a modern one typically has these lookup tables. It has muxes for muxing different values. But the other thing that they have registers to register the outputs, but often what they also include are these carry chains. And this is special logic. So for instance, let's say you want to make an adder. Let's say you want to make a ripple carry adder, which you guys have done already, I think, right? So you have like, this is 4 adders, and there's like A and B inputs, right? And then there's C outputs, but then there's also this carry chain, C out, right? Well, you know what? Those C outs, if this 1 adder block was in 1 LUT, and then you had to wire it out through this switching matrix to another block. then you can get a lot of delay if you're going through the switching matrix. And people realize, oh, if I build adders, they're really slow because there's a lot of delay in this carry out, and I need this carry out to propagate. So what they said is, oh, let's improve that. We're going to put these carry chains. And so I can have a bunch of LUTs, but there's a carry chain which is hardwired between them. It doesn't go through any switches. And they're used for counters and for adders and all kinds of things. And that's built right into the hardware. That makes sense? Okay. And there's different slices that have different configurations of this. This is just showing what the programmable interconnect looks like. So here's a CLB, bunch of CLBs here. Here's the switch matrix. The switch matrix is usually some crossbar switches. So for instance, we have a bunch of inputs coming in here, and I can pass them to any of these outputs, depending on how I configure these little diamond shapes. And the diamond shape is basically a bunch of switches that either pass, here's my input. If I control this one, I can go this way. If I control that one, I can go this way. If I control this one, I can go this way. So I can go whichever way I want. And each one of those switches has a little programmable memory, and that's the memory that configures it. And those are what we call local interconnects. And those are used for just interconnects from one block to another. In addition to those, we usually have what are called global interconnects. And they are for like signals that pass across a large part of the chip, like clocks, sometimes resets, anything that needs to go to a large number of blocks. Instead of using these, we'll use the global interconnect wires. I'll show you a picture of that in a second. Yeah, so here is a slice which has a bunch of LUTs in it. Here is the interconnect switch box that makes the connection. And then there's a bunch of local connections inside here between all these blocks. But then we also have these global vertical routes, both horizontal and vertical, and they can go to many blocks inside of all of these switches, okay? And then each of these, there's a big massive array. So these global interconnects are running all the way down. And these are all, each one of those is one of these. And there's literally thousands and thousands of them. And if you go into the Vivado software, you can actually see this view, and you can go in and look, and it'll show you where the interconnects are made. And this is when you do the place and route, it's putting your logic into some of these blocks, and it's routing the connects, either local interconnects or global interconnects. So this is like directly a screen capture, like from Vivado software. Yeah. And there's all kinds of different clocking. There's single-ended buffer clocking. There's differential buffer clocking. There's global buffers. There's regional buffers and local buffers. So I said there's global routes that run the whole length of the chip, but there's also local just between the parts of a slice, but there's even regional, like, okay, this whole region has a set of signals that route to it. So they found by making some hierarchy of dividing up the clock signals, they can sort of optimize the speed and performance of the FPGA. So there's all different kinds of clock regions. That's kind of mostly invisible to you. Like basically the software decides how am I going to route these things to optimize it. We mentioned there's DSP resources. This is just an example of a DSP. I think one of the labs you do use a DSP. So you can make digital signal processing out of the logic and the flip-flops. But what's nice is there's little hardware, little blocks that are built that are much higher speed. And here's an example that a DSP slice that has adders and subtractors. It has a built-in multiplier. Remember we said multipliers are really hard to do in FPGAs or in logic and period in Verilog, but there's built-in little multipliers in there that we can use. And there's little accumulators and pattern checkers and stuff. So this is all built in. It's like an ASIC. It's all built with all the routing for all this is not through switches. It's just wires, and the whole thing runs at really high speed. So if you need some DSP resources, you have them on the chip. You kind of go back here. Yeah, you would, you might have some logic in here, and you say, oh, I need to do some add of these two logic blocks. Well, you route them in here, and you do the add and the multiply over here, and then route that back into the memory and store it. I don't know, you can do all these kind of things. But you could do the DSP in these logic blocks, but it would take a lot of them and it'd be much slower. And there's literally hundreds of these DSPs, thousands in some chips. So it's amazing how powerful these chips can actually be. So those are DSPs, and you can mux them in. So you can run this. These things run at, remember I said the Fpga runs at maybe 100, 200 megahertz. These things run at like 500 megahertz or higher. So often they run much faster than you can run the clock. And so often we mux them in, like we do two little multiplies in here in the time that the other clock runs. So usually they kind of like they're double up data rates in some cases. You don't have to do that, but often you do. The next thing we're going to talk about, this is an example of an FPGA. This is not the one we're using in our lab, but this is an Intel Cyclone FPGA. It's a little older generation, but it has kind of a good picture to kind of show what things are on it. So you have I/O blocks, which are programmable blocks. We'll talk about those in a minute. We have these logic arrays, which have all the CLBs. So there's all kinds of CLBs in here, right? Many, many, many of them. And there's lots of different logic arrays. There's embedded multipliers. So these are kind of like your DSP blocks in here in the middle. And then there's memory blocks. So these are like chunks of memory in here. This is like a high-level block diagram. Then there's this other thing over here. This is really important. This is called a PLL. Does anybody know what that stands for? PLL. I'm going to be talking more about this. That stands for phase lock loop, okay? PLL. And these PLLs are super important. You've been using them all along. You didn't realize it. On the FPGAs we have in the lab, we have an external 100 megahertz clock, right? There's a little chip that generates 100 megahertz. And basically it comes into this divider block to the PLL, and the PLL generates I think we've been using either a 5 megahertz or 10 megahertz, right? So it's the first block. PLLs are kind of cool. You can make divided down clocks and you can feed it around the chip. You can also multiply the clock up. So you can generate a 200 megahertz clock with that, increase the frequency. That's the more common case that we use for PLLs, because it turns out if you want to get a high-speed clock, once you go above 100 megahertz, it's hard to get in through the pins of the chip. And if you want to, for instance, a 500 megahertz clock, well, it's impossible to bring it into the chip from a pin almost. So we use a PLL. We bring in this low-speed clock, and then we multiply it up to clock our whole chip, okay? The other thing that PLLs do, and hey, Prof, just a quick question. Vivado and Quattros, which you think is better? I don't know. I haven't used Quattros much lately. Vivado was like, Xilinx was definitely the leader for a long time. Now, Quattros was Altera, got bought out by Intel, and Intel kind of improved it a lot. So they have some cool chips right now. We'll look at some of the specs of it. It's always a battle between Intel and AMD now, or used to be Altera and Xilinx. I don't know which is better, to be honest with you, but I do know Xilinx, what we're doing in the lab, definitely has a larger market share, and it's been more popular over the long term. Anyway, getting back to these PLL, so they're great for making divided down or multiplied up frequencies. The other thing we're going to see when we talk later about clocking, getting a clock around your chip that is synchronized is hard. Like if I have a clock signal that's coming here, and I want that same clock down, say I'm coming in here, I have a little block here, I want a clock, and I want the same clock to get here. Well, we have these global routes, which is great. We have these vertical and horizontal routes, so I could have the clock go there. But these chips are like, a big chip today is 25 millimeters on a side, okay? That's 25 by 25 millimeters. Now that doesn't sound like much, but the speed of signals on a chip today, it's not quite the speed of light because you have a dielectric, but you're looking at about 100. I always remember this in inches. I don't know why. 100 to 150 picoseconds per inch. So what is that? Per a millimeter, what's it in? That's 25, right? 25 millimeters in an inch, right? So let's divide this 150 by 25. That's about 6 picoseconds per millimeter, right? So if I go 25 millimeters here and 25 millimeters there, I've gone 50 millimeters from one end to the other. Then I've gone 300 picoseconds. Now we already know that's 300 picoseconds delay, getting this clock signal from here down to here. We already know, like, we're trying to build circuits that run like with delays of 10 picoseconds, 5 picoseconds. This is huge. And this is just the speed of light traveling on a wire, okay? You guys are the picosecond generation, and things are going really fast, okay? You're like at the speed of light almost. So we need a way to deal with this delay. We call this clock skew when we're going from one end to the other. And these PLLs come in really handy for that, because these PLLs, in addition to multiplying the clock, they can change the phase of the clock. They can add delays. So I could have this clock signal come in here, and I could have the clock signal come in here, and I could say, oh, you know what, make the same clock frequency here, like maybe it's 5 megahertz, maybe it's 20 megahertz, whatever, but I'm going to add a little delay here, and I'm not going to add any delay here, so that, you know what, the clock is arriving at these two blocks at the same time. I can kind of cancel out the clock skew. So these PLLs are really cool that way, to do that kind of thing. What's the difference between a PLL and FLL? An FLL stands for frequency lock loop. And there's also a thing called delay lock loop. There's 3 kinds of categories. The frequency, the phase lock loop compares the phases. So here, where we want to get the right clock phases, super important to have a phase lock loop, okay? To line up the phases so the clock edges are lined up. Frequency lock loop says, I don't care about the phases, but I'm going to make these the same frequency. So yeah, I could have a 200 megahertz here and a 200 megahertz, but I don't know a relationship between the edges. So they're a little simpler to build, but not as powerful. And the delay lock loop is kind of like a PLL. You can line up the phases, but it can't multiply up or down. It just uses the same frequency. So the PLL is kind of the best of both of these. It gets the phase alignment of a delay lock loop, and it gets the frequency multiplication ability of a frequency lock loop. So these are more commonly used than anything. And I always tell students, if you ever want to learn something in your undergraduate, learn as much as you can about PLLs, because they're in every digital chip that people make today, and they're in every analog chip or mixed signal chip, because they're so powerful to do these kind of things. That it's basically, and this is a lot of my research is on PLLs. They're super good to learn as much as you can about them, because you will, if you become a digital designer or an analog designer, even if you're just do software, you're going to run into these PLLs, programming them or whatnot. So it's good to understand how they work with it. Okay, any questions about that? Nope. Next slide. Well, so this is the FPGAs that we're using in the lab. We're using the Vertex 7 series. That's a little bit old. I think it's 10 nanometer technology, or maybe even slower. I'm not sure, but it's a few generations old now. We're using this Arctic 7 family right here, which is kind of the low end in terms of cost, because, you know, it's just for educational purposes. But you can see some of the specs here. There's 360,000 logic cells in it, right? So you know, this is one logic cell, or a CLB, right? So we have 360,000 of them. So we got, you know, like almost 1 million flip-flops. We've got, you know, 1 million little logic blocks that we can create logic with. So that's a lot, okay? That's at the kind of the low end. It's got 9 megabytes of RAM. It's got 1,000 DSPs. So think about it. Each one of those DSPs is like a little ALU. So like, you know, you have your quad core Intel i7, right? Maybe you got a 16 core. People say, oh, I got a 16 core i7. Wow, I can really move along. Well, on this FPGA, you could say, oh, I've got a 1,000 Core i7, right? Low end still worth more than $300 US? No, they're cheaper than that. I'll show you some cost the numbers later on, but you can get them. The RTX 7 that we have, like the whole board is maybe less than $300. So the chip on it didn't cost maybe half of that or something. I don't know. Anyway, 1000 DSP. So you can do, this is G max is giga multiply and accumulate. So that's a gig is a 10 to the 9 multiply accumulates, and you can do 1,000 of them. So you can do a tera max. So 10 to the 12 multiply accumulates per second on these FPGA. Yeah, maybe university got it for bulk price. Yeah, universities get a discount. You're right. So I don't know, but they're not super expensive, and there's cheaper versions. These are super expensive up here. These are like thousands of dollars in some cases. You can have high-speed serial links. I don't know, I'm not going to go into the details, but lots of bandwidth up to a gigabit per second going in and out of the chip. You have different power supplies. You can have up to 600 I/O pins, and you can have different package options. But anyway, that kind of gives you a little bit idea of the specs of this chip. At the high end, these are like 2 million logic cells, 68 megabits of RAM, 3,000 DSPs, higher DSP ability, higher IOs, higher IO bandwidths, and so on.
Is there also a difference in feature sets in between all those boards?
These all use the same technology, and they all have the same basic. Just as you move along, they get more of it.
Okay. Because I heard that as you increase in price, you get more features on the board, not only just numbers.
Maybe a few features, but they generally have the same features. It's just like, oh, instead of 16 transceivers, I have 96 or something. You know what I mean? What does GMAC represent? GMAC, so a multiply accumulate is called a MAC. Okay, so in our little picture back here, this can do a multiply here, and it can do an accumulate. You can either add things here or you can add things here. That's called a multiply accumulate. So it's a very in many DSP functions, like say you're doing image filtering or something, you would multiply by a weight and you would add all the values together. It's many digital signal processing. That's the basic unit. Okay, so a giga multiply accumulate means 10 to the 9. Okay, it can do 10 to the 9 of these per second. And 1,000 of them means, oh, it can do 10 to the 12 of these multiply accumulates in every second. To give you an idea, say you have a 2 gigahertz i7 or i9 processor. It can probably do one every clock cycle. So it can do 2 times 10 to the 9. And if you had a 16 core, you could do 16 in parallel. You might do, if you have a super expensive quad core, it could do 32 times 10 to the 9. Okay. This one chip can do 10 to the 12. So, it's another order of magnitude faster than a 16 core i7 or i9 processor. So it's super powerful. This little chip here, which costs a fraction of an i7, like a quad core i7 chip, can do a lot of stuff. And that's even though it's programmable, and it's programmable to do all different kinds of stuff. This one out here can do even more, right? These are some specs from the Intel. This is I forgot to mention. Another thing that's been added in the latest generations is they put, in addition to all this, they put whole processors. So you'll see they have, like, if we back up here, in addition to like DSPs, you can have like interconnect, and you can have like an ARM processor, a Cortex processor, and sometimes they'll have multiple of them. So you have a whole ARM processor. So you can make a processor out of this logic. It's pretty slow, but these also have like a hardware built ARM processor that runs at 2 gigahertz. So you can have multiple of these ARM processors plus all this other stuff. And so you can use the ARM processor to be super flexible, do whatever you want the program to do, plus all this high-speed DSP and memory to accelerate any kind of function you want to do. And that's, for instance, this Intel Stratix 10, it's in 28 nanometers, so that's pretty old now. Oh no, sorry, that's the old one. It's in 14 nanometers. So still, today we're at 7 and 5. We just started doing 5. I have an Intel Cyclone SSD, costs $400. Cyclone 5. Yeah, I don't know where Cyclone 5 fits into the Stratix was their high end. Cyclone was a little lower end. But Cyclone 5 may be better than the 7. But this was 14 nanometer technology. So it had 4 ARM processors on it. It had, which run at 1 gigahertz. It had 2 million logic elements. It has 90 megabits of memory. That's just single bit memory. And then it has 229 megabits of these 20K bit memories. It has 11,000 DSPs basically. And it has floating point functions that can do 9 teraflops. So it's got a floating point blocks in it. It has up to 144 transceivers. It's got 12 gigabit per second data on the pins. It has PCIe connections. It has multiple PLLs. And yeah, so, and this is older now. This is 14 nanometers. So today's 7 nanometer even has more. So lots and lots of features in these FPGAs to do lots of stuff. So they're very popular. Anything like almost any, they're not so good like in a handset because these take a lot of power. So things that are really battery powered, not so popular. But anything that's plugged in, like a motherboard for a desktop computer or a base station for cell phone towers, they're using these FPGAs all the time. Super powerful, super flexible. The other big place that they use them is in data centers all the time. They said, I think Intel line update quite quickly than Xilinx. That's pretty much update every 2 years. Yeah, they've been doing a lot. And mining, yeah. Well, so the history of crypto mining first they went with processors, standard processors. And then they went to, oh, that's too slow. They went to FPGAs. And they said, oh, well, actually, first they went to GPUs. GPUs are better than a processor. It's got more processing elements. And they said, oh, that's not fast enough. Then they went to FPGAs. And then finally they said, oh, let's do this in ASICs. We can really mine. Yeah, so today mining is done almost exclusively with ASICs. So the last thing is the programmable IOs. This just shows an example of a programmable IO. So here's our pad, and it can be a input or an output. So if we're coming in, there's a buffer that can choose either CMOS or TTL. This is a kind of a low speed standard pad. And then there's this block that comes in and it's programmable. I can either feed the signals directly in, or I can have a latch or a flip-flop to clock them in synchronously. And then on the output side, we have our famous tri-state driver we've learned about. So it can be either drive the pad or it can be turned off, disabled. It has slew rate control that's for high speed. We might talk a bit about that. When you have transmission lines, sometimes you want to control the slew of it. And the signal coming out can either be direct logic or it can have a flip-flop here to clock it. It has this pull-up. We learned about this before. Remember we talked about wired OR? So you can program that. Remember we had this idea I told you. Often we'll have one chip connected to another chip, and they're wired OR, and we'll have this little resistor. And so inside here, there's just one transistor here, and there's one transistor here. And I can pull it low with that transistor, or either one of them can reset it. Well, putting this resistor on the chip is kind of painful. So these FPGAs say, oh, I don't like those external resistors. They say, let's build a little weak pull-up transistor inside the chip, and that acts as, so that's turned on, but it's very weak. So either this can pull the pad down or some other chip can pull it down. So there's lots of features built into these little IOs that are programmable, and you can program to choose what kind of state they will operate in. So these are for older technology, and I think I explained to you before that today, in the old days, my day, early days, and grandma's days, what people did was, if I wanted to connect from one chip to another, and I wanted to send a lot of data, I would have basically a register here, and I would clock that register. These are a bunch of pins on my chip. I have another chip, and I would send this wire across to this chip, and over on this chip there would be a pad. This is my clock, and there'd be another flip-flop, a register over here, and this register would be clocked by this, and there'd be a bunch of pins here. And these wires would go between the chips, okay? Now, I might have a bus that's 32 bits wide, or I might have 64 bits. I don't know, bigger than that, it gets a lot of pins. But anyway, this was my clock, and all this stuff is data, right? Well, it turns out if I send a clock across between these chips, and this is going from one chip to another chip on a board, it kind of tops out at about 100 megahertz, okay? So let's say I have a super big bus. It's 64 bits wide. So I have 64 times 100 megahertz. That's my maximum data rate, which is 6.4 gigabits per second. Okay, and that's using a lot of pins, a lot of package pins, a lot of wires. Today, what people do is they say, oh, let's have this chip, and I'll just have, well, I'm going to use 2 wires. I'll tell you why in a second. I'm going to use 2 wires. And those wires, what goes on them, let's just look at one of them, is a signal that looks like this. And if it's representing a 1, it'll clock one way. And if it's representing a 0, it'll not clock or whatever. But inside this, there's a signal. You force the signal to toggle every so often. You can encode the signal so that it's always got a transition at some time or another. And on the other side here, so this is the coming out of here. So on the other side here, we have a clock and data recovery circuit, a CDR. And what it does, it says, oh, you know this signal here? There's a signal, there's some data values, like maybe this was a 1, and this was a 0, this was a 1. But there's enough transition so that it recovers the clock locally. So the clock and the data are embedded with each other. And when I do that, it turns out I can go much faster. See, the problem we had up above here is, these wires aren't perfect. This wire has a little bit, this distance is the distance on these wires is different as I route them between chips. So when the clock is going like this, and I'm trying to make this a really small period of time, like so less than 10 nanoseconds, well, the different delays mean that the data arrives at different times, okay? So we want the data to arrive right here in our restricted, before our restricted region, right? But if some of them are too late, they come later, I don't catch them right. So that limits the speed. Here, because the clock is embedded with the data, I don't have to worry about that. It's all on one line, and so I can recover that. So how fast can this go? Well, 2 lines today, the chips that I'm working on go at 224 gigabits per second on 2 data lines, okay? So that's, this was 6, this is at least, this took 65 lines. This is 2 lines, is going 20 times faster, 20x. And so, and with a lot less real estate, a lot less wires, and a lot less power. The reason there's 2 lines is because these signals over here swing, like say from 0 to 1 volt. These ones tend not to. They have smaller transitions. These signals might swing maybe 100 millivolts or something like that. And when you have this smaller swing, if there's noise coming from outside from other chips, or if interference from radio signals or whatever, they're not as immune. Remember, we learned that standard CMOS is super reliable. We have this large noise margin. When we have a smaller signal, there's less noise margin. So we send it differentially. And what does differentially mean? It means, oh, when one signal is going high, the other signal is going low. So these are the, these signals are the opposite transition. They're differential opposite of each other. And on the other end, we decode it differentially. I'll show you how you do that in a minute. But the nice thing is that when we have this interference coming from outside here, you know what? This signal goes up a little bit, and this signal goes up a little bit because of the interference. But the difference between them doesn't change because they both see it. That's what's called a common mode signal. So when we're measuring the difference, if we have all kinds of noise here, we're almost immune to it. So by making it differential, we can go super high speed and we're immune to any noise. Because as you go higher speed, higher speed, noise becomes a bigger and bigger problem. So we need this to give us immunity to noise. So go back here. So this is how you would build a differential. So for instance, low voltage digital signaling is a common standard, and it uses a 50 ohm transmission line. You have to terminate it with a 100 ohm resistor differentially, and then you have a differential, basically an op amp kind of circuit here that measures the difference between these, not the absolute value, and that recovers the data. And in fact, if it's got a CDR, we can get the data and the clock coming out of it. So that's how people transmit data today at much higher speeds. So standard I/O supports all kinds of things. Today, for really high speed signals, they use differential signaling. And you have to be very careful about switching noise. That's why it's differential. And it's all kinds of standards, like PCI for your connections from in your PC to memory, fiber channel, high-speed Ethernet, they all use this differential signaling. And in fact, if we back up here, these transceivers here that are going at 6 gigabits per second, those are differential signals that are going here. So those are the IOs. Any questions about that? Okay,